Hi, everybody. Now let's prove some very simple first facts about groups, which clear up some ambiguities which are left over from the definitions. In mathematics, you often try to give the smallest possible set of axioms for something, as a result, some other facts which you might have thought would clarify things if they'd been included in the axioms get left out, and it becomes our job to establish those facts. So we're going to prove our first few theorems using the definition of a group. So the first thing that we're going to take up is a question which has to do with whether or not there could potentially be more than one identity element in a group. So remember the three axioms for a group: that the operation is associative, that there's an identity element, and that every element has an inverse. So one thing which is not said is, could it happen that a group has more than one identity element? The axioms just say that there is an identity element, but they don't say that there's only one. But in fact, it turns out that the other axioms, together with the fact that there's at least one identity element, is enough to tell us that there's exactly one identity element. So the question is, could there be two elements, E1 and E2, in the group, which are different, which have the property that E1G is G, E1 is G for all elements of G, and E2G is G, E2 is G for all elements of G. In other words, could there be two different identity elements? And we're going to prove that that can't happen. We're going to prove the proposition that if G is a group, it has exactly one identity element. And our strategy for this is to suppose that we had more than one, suppose we had two, and show that in fact those two supposedly different elements are really the same. And we're going to do this a step at a time. So we begin by assuming that E1 and E2 both have the identity element property. That is to say, they both satisfy the equations E1G equals GE1 equals G for all G, and E2G equals GE2 equals G for all G. And let's see if we can use those equations to show that E1 is equal to E2. And the trick is to plug in E2 for G or E1 for G and see where that gets us. So first of all, we know that since GE1 is equal to G for all G, that's the identity element's property. In particular, if we take G equal to E2, then we would have E2 times E1 is equal to E2, because that's true for all G. On the other hand, E2 is also an identity element, and so it acts on the left. We know that E2G is G for all G. And so for that one, we can choose G equals E1, and we get E2 E1 equals E1. But if E2 E1 equals E2 and E2 E1 equals E1, well, then E1 equals E2. So we've shown that if you have two potential identity elements in the group, then in fact, they have to be the same element. And therefore, the identity element in a group has to be unique. A similar sort of question has to do with inverses. So the axioms of a group say that for every group element, there's an element, every group element G, there's an element H, which acts like a multiplicative inverse. That is to say, H times G is the same as G times H is E, where E is the identity element. It doesn't say that this inverse element is unique. In other words, it could happen that there were two inverse elements. There could be an H1, so that H1G and GH1 were E, and an H2, so that H2G equals GH2 is E. The axioms don't rule that out. However, we're going to prove the proposition that there's exactly one H so that hg equals gh equals e for all g. In other words, if we have an element g in G and we write G inverse, meaning the multiplicative inverse, that's a well-defined element. There's only one multiplicative inverse. And the proof is very similar to the earlier one, namely we suppose there are two, and we use the properties to show that in fact they're equal. So suppose we had a G in G, and suppose it has two multiplicative inverses, H1 and H2. Well, that means that H1G is GH1 is the identity element, and H2G is GH2 is the identity element. Here's the, if you like, the trick to the proof. We take H1 times G times H2, and we're going to use the associative law to read this in two different ways. On the one hand, it's H1G times H2, and H1G is the identity element because H1 is an inverse of G. So H1G H2 is the identity element times H2, and that's H2 because the identity element times anything is that thing. On the other hand, if we use the associative law, instead of doing the calculation as first H1G, then H2, we do H1 and then we do GH2 first. And since H2 is an inverse of G, GH2 is also the identity element, and so we get H1E. And since E is the identity element, H1E is H1. But if you look at these two equations, what we've shown is that H1GH2 is equal to H2 from the first calculation, and it's equal to H1 from the second calculation. So H1 equals H2, and therefore there's only one inverse element. And it makes sense when we have an element G to write G inverse to mean the unique multiplicative inverse. Next, we want to think a little bit about equations. I mean, where would we be in algebra if we didn't have equations? And an example of an equation in a very abstract sense is, suppose we have H and G, which are two elements of a group, and we want to know, is there an X so that H times X equals G? And in other words, we want to solve this equation for X. And the proposition here is that you can always solve this equation. Namely, if you have Hx equals G, you can always find X that satisfies this equation. And also remember that multiplication, the order matters. So you could also look at XH equals G, and that also has a solution. And here we see sort of algebra at work. If we look at the equation Hx equals G, then we multiply on the left on both sides of this equation by H inverse. And we get that H inverse Hx is H inverse G, and we use the associative law to regroup H inverse Hx as H inverse H times X. But by definition, H inverse H is the identity element, and the identity element times X is X. So we have the solution X equals H inverse G. If you did this in the other case where you have the equation XH equals G, then you multiply by H inverse on the right, and you get X equals GH inverse. Now, if you were just doing regular old algebra, and you maybe with rational numbers or something, and you had the equation Hx equals G, you would think, okay, well, the solution is G over H. And in a certain way, that's true in a group, but you have to be super careful because G over H doesn't make sense unless you're clear about which side H is on. And that's because you notice that in one case we have the solution H inverse G, and in the other we have the solution GH inverse. In some sense, those are both G over H, but they may not be equal to each other. So we can't just work with fractions like we do in the case of rational numbers, because our multiplication isn't necessarily abelian. And finally, This is more or less just a notational trick. I'm not going to work it out in painful detail, although I probably should. But we can use exponents when we work with groups. And when we write g to the n, we mean g times g times g n times. That makes sense because of the associative law. No matter how you group those g's, you get the same answer. And we let g to the minus n stand for g inverse to the n. And if you make those definitions, then the laws of exponents hold. So for instance, you can just check g to the minus 3 times g to the 5th, for example, is g inverse, g inverse, g inverse, g, 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 g. And now you use the associative law. These two guys cancel to give the identity element. But the identity element doesn't change the product, so we can kind of forget about it. And then these two guys cancel, and then those two guys cancel, and you're just left with g squared at the end, as you would expect. Now, one thing to bear in mind is that if you take the inverse of a product, it reverses the order. For this one, let's just check. GH inverse is the element of the group, which when you multiply it times GH, has to give the identity element. And notice that if you take H inverse GH, then again, this is H inverse GH, which is H inverse EH, which is H inverse H, which is E. And that shows that H inverse G inverse is the inverse of GH, and there's only one. We already know that the inverse is unique, and so it must be the case that the inverse of GH is H inverse G inverse. The last comment is that if you're in an abelian group and you take GH to the n, then that's G to the n, H to the n, but only if G is abelian. If G is abelian, then strictly speaking, what is GH to the n? It's GH, 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 n times. If G is abelian, the order of multiplication doesn't matter. We can pull all the G's to the beginning and all the H's to the end, and therefore we would get G to the n, H to the n. But if G is not abelian, you can't do that. You can't move the G's past the H's. And in fact, this is false in general if G is not abelian. We'll see some examples of that later, but you can even see it with matrix multiplication. If you can work out examples of matrices where the multiplication isn't commutative, and you can see that that's not true. So those are some of our basic facts about groups that we're going to take advantage of as we do some more algebra later on in the course.